So it's a pleasure now to have Alessandra Bianchi from University of Padua, who will speak about limit theorems for exponential random graphs.
So first, I would like to thank all the organizers for their great job and for taking care of everything. I'm very happy and joining this event. So the work I'm going to present is made in collaboration with Francesca Collet from the University of Verona and Elena Magnanini from the Weierstrass Institute of Berlin. And it's a work about exponential random graph. And at first, I want to describe the setting and the very basic definition. Exponential random graph are models of simple graph. So I will denote by Gn all the family of simple graph on n vertices. This is the symbol for vertices labeled from 1 to n. So a general graph which is identified by a set of vertices and edges. As a vertex set, this set of vertices, and as an edge set, a subset of the family of all possible unordered couple of distinct vertices in N. Okay, now exponential random graphs are defined by setting a measure on Gn. In particular, this measure is a Gibbs measure. Okay, so in particular, it's defined through an Hamiltonian. The idea is, in general, to construct a measure that is able to announce or decrease the presence of a specific graph structure in the ending graph. For this reason, the family of exponential random graph is very big because there is a lot of freedom, a lot of parameters that might enter depending on which structure one would like to control somehow. And for this talk, I will focus just on a simple on one model of exponential random graph, which is the edge triangular model, which is one of the most indeed studied and used in application. It's also called Strauss model because it has been introduced by Frank and Strauss in a paper from the 80s. So it has a long history because immediately all the family exponential random graph attracted the attention of the network community, but also statistician community and statistical physics community. Lastly, as I will show you, in the last 10 years, also mathematician starts to provide very important rigorous results and when there are very important contributions. So as I said, the measure that characterizes this family is a Gibbs measure. Hence, we have to fix parameter alpha and h real parameter. And then the measure of the probability of a given graph is exponential in this Hamiltonian. We have a normalization constant that, as usual, is called partition function. And the Hamiltonian is described here, is essentially a combination of a count of triangle. This is the symbol, I hope it's clear, of triangle in the number of triangle in G. Okay, this is very sensitive. And this is the number of edges in G. Okay, and this count is weighted with these two parameters, alpha and h. And of course, since alpha and h are real, by tuning this parameter, one can somehow control the property, the final property of the graph. Notice, however, as a remark, that when alpha is equal to 0, then so when you don't have anymore this term, the Gibbs measure is just exponential in the number of the edges. So this means that it precisely corresponds to the Erdős-Rényi measure with parameter np, and in p is a function of h. Okay. This means somehow that this model generalizes and contains a particular case, the class of Erdős-Rényi, by introducing dependencies, because okay, Erdős-Rényi graph, edges are taken in the graph with independent probability. Okay, so we have now a generalization, and the term that provides an interaction when alpha is different from 0 is precisely the count of the triangle. And this dependence is this interaction between edges, a three-body interaction. This is probably more clear with the next slide. Let me maybe stress this fact that in general, the family of exponential random graph are defined classically by using homomorphism density. So for this talk, there's no need to enter in this generality that will force me to give a lot of definition. But let me stress that this Hamiltonian corresponds precisely to the representation with the homomorphism density. It's precisely the same. Fine. So as I said, probably a better way to see the interaction between edges is to produce this representation. Now, simple graphs on n vertices are just specified by their edge, the set over their edge, and hence we have a bijection between Gn and this set of assignment of 0, 1 to the edges, to the all possible edges on n vertices. So if I denote this underline x as this assignment, I will call configuration. Since that we have this bijection, we can just bring our referring measure to this set of configuration, and when we translate the Hamiltonian of the system in terms of this underline x, which is a collection of 0, 1 indexed in En, we have something that really recalls a particle system. And now you see that the interaction here is in between this summation here. The summation is over edges ijk, so now ijk are labeled for edges that possibly form a triangle over n point in a complete graph. I denoted here the set of triangle of the complete graph. So you see that you have a contribution of 1 if this the product of xi, xj, xk is equal to 1. So if you have all the edge there. So this is precisely the count of triangle, or this is the second term is the count of the edges. The goal of our work is to determine the limiting behavior of the edge density. So the number of edges divided by n square over 2, which is something that take value in 0, 1, in particular in this discretized space, which step of 2 over n square, whatever. Equivalently, maybe using a terminology is more easy for probabilistic. If we let this underline x be our vector of Bernoulli variable, having in label in En with the joint law Pn alpha h, and denoting by Sn their sum. Okay, now the edge density is precisely the empirical average of this random variable. Okay, now before moving to the results, let me present some relevant results that have been obtained before. First, the first basic result I want to mention is what concerns the free energy. The free energy, you see here the definition. On the right, you have a finite size free energy, and on the left, the infinite size free energy. So essentially, you take the logarithm of the partition function, you divide it by 1 over square. We know that the free energy is very important because it's able to characterize in the limit, so somehow the macroscopic behavior of our graph. That is the maximizer of the measure in the limit as m goes to infinity. And however, is very important even in statistics because it is a fundamental tool for implementing maximal likelihood method. For example, so the very important results that I want to recall is this one by Chatterjee and Diaconis of 2013, which is is a general, so it applies to all the family of exponential random graph, but here I'm providing the results for our specific case, because now the hypothesis is very simple. Take alpha bigger than -2. Okay, then the free energy happen to be completely characterized as a solution of a one-dimensional problem, maximization problem. So it's the supremum for you in 0, 1 of this function. If I arrive to speak about the midfield approximation, maybe you might realize where it came from. So in particular, if I denote by U star the maximizer, this is just a function of this explicit function of the U star. Okay. Now, the point is that the maximizer need not to be unique. When it's unique, okay, however, they prove that the set of maximizer is finite, and in particular, in these two cases, just provided by two values. When it's unique, what we prove is that in the limit as n goes to infinity, then the edge triangular model and the Erdos-Renyi with parameter u star, which is the unique solution of the one-dimensional problem, behave in the same way, which means that asymptotically, essentially, they converge to the same structure, which is a graphon in the terminology of graph limit theorem. But for the moment, just think that they are really indistinguishable, as I said. While if U is not unique, so we have to essentially to maximizer, then it turns out that in the limit as n goes to infinity, the measure is a mixture of measure. Okay, it's a random mixture of measure. So essentially, it behaves like a Erdos-Renyi with parameter u, where u is randomly chosen from the set of maximizer that are two. This one, the distribution. Ah, nice question. This is open in the sense is not the constant is not is unknown, and in fact. We have conjecture on this. No, because so when one look at this result, one might think to co-revise model or like Ising model in a situation of phase transition. What is missing here is the symmetry, because the random variable are Bernoulli random variable. There is no symmetry, and so you cannot easily deduce for Ising for co-revise you have 1/2, 1/2. But here there is no symmetry, so this argument failed. Okay. In their paper, they say essentially of course. Okay, we will come back there. Are there other questions?
Do you know anything about the global feature of the graph, like giant components? So given alpha, is there a critical age for?
Ah, okay, yeah. Like thank you also for this question. The exponential random graph is a dense graph, so. You have a number of edges that is proportional to n squared, so there is for sure a giant component. Yeah, but thank you, because I didn't specify that.
So there is also a question from the chat. Do you know the graph of critical curve in alpha h?
I'm going to do that. Okay. Is just the next results. So now the point is, so thank you. The point is, of course, one wonder when, okay. The natural question when this maximizer is unique or not. So let us focus on the phase diagram in alpha in H. Here I am reporting some results obtained in Chatterjee Day and Radin Him. Okay, no, so let us call by the node by RS that stay for replica symmetric regime, the couple of parameter alpha and H such that alpha is bigger than -2, so that we are in the situation where the theorem of Chatterjee and Diacon is applied. Okay. Now, of course, this split is an uniqueness regime. This region is, of course, all this half plane on the right of the value alpha -2. Now, of course, this region has a uniqueness, can be split in a uniqueness and a multiplicity, this M stay for multiplicity region. And so it turns out that there is a critical point, alpha C HC, with explicit coordinate. Alpha C is equal to 27.8 and AC log 2 -3/2. This critical point is in the uniqueness region, but from this critical point, there is a curve, Q alpha, which is not explicit, but qualitative, as it is in this picture, that correspond precisely to the region of multiplicity. So essentially, in the replica symmetric region, we have always a unique solution, but on the curve. It's the following results by Radin Hin of 2013, where they show that indeed this free energy is analytic in all the uniqueness regime, but we have to exclude the critical point. At the critical point, as a second order discontinuity, while in the multiplicity region, it has first order discontinuity. Here I just put a picture taken from the paper of Chatterjee and Diaconis, which is due to Sukada Fadnavis, where it is represented the solution U star as is this surface that depend on the two parameter alpha and h. Here is written beta 1, beta 2 because this is they use different parameterization, but it's the same thing. And you can see that there is a cut in this surface corresponding to the curve, to the multiplicity curve. Fine, let me go to the results. As I said, the results are about the behavior of the Sn, of the density of the edge. So at first we proved that, well, if we look at the convergence of this object, this empirical average, so we derived a strong law of large number with respect to the measure of our edge triangle graph. So that is an almost surely convergence to U star, which is the unique solution of the problem. Okay. Of course, okay. While in the region of multiplicity, we cannot hope for such a result, but however, we prove convergence to a mix in distribution, to a mixture of delta Dirac measure on U1 star and U2 star, where k is unknown, as I said. This is the same unknown constant also present in the paper of Chatterjee and Diaconis. We can, of course, when one has a strong law large number, one might wonder about the speed of convergence, of this convergence. So we are working on that, even because it was somehow an instrumental results for the study of the model. So essentially what we proved is that in a sub-region of the unique regime, because this is just a strip of value where alpha is in between -2 and the critical point, well, this speed of convergence is of order 1/n, but up to sub-polynomial correction, because here there is this exponent epsilon. While at the critical point, similar results, essentially the speed of convergence is of order 1/√n up to polynomial correction. Okay. First set of result. Then we move to study the fluctuation. So in the uniqueness regime, we have a strong law of large number. We can somehow control the speed of convergence, and then we look at the fluctuation of Sn around this average. For that, let me introduce the following object. So we have Mn. It is the average density. So it's precisely the average of 2Sn/n squared. And of course, it depends on alpha and h. And Vn, which is the derivative with respect to h of Mn. This is called variance edge density. This term is ambiguous here, but the point is that, in fact, the average edge density can be shown to be equal to 2 times the first derivative in h of the finite size free energy. This is by a direct computation. Okay. And hence, Vn is 2 times the second derivative of the same object, this finite size free energy, and that by a direct computation is shown to be this variance. At least give a sense to this definition. And the result is the following. Well, if we are in the uniqueness region excluding the critical point, then we have this standard central limit theorem. So we take Sn, we subtract this average, and we scale this quantity in a diffusive way. Recall that Sn is a sum of n squared over 2 random variables. Okay. And the convergence is to a central Gaussian random variable with this variance, where the variance is the limit of the variance edge density here. And in particular, is precisely 2 times. Like here is precisely 2 times the second derivative of the free energy. And from this, you can realize that in turn is precisely this quantity. From this, you can realize that these results cannot be moved up to the critical point, because at the critical point, this second derivative It's not well defined where the result break. And but we have conjecture on that. And the conjecture, if maybe I have a few minutes, I will go to that, are based on two arguments. A mean field approximation argument that might be of independent interest because it's a kind of toy exponential random graph, and a large deviation argument. The conjecture is that at the critical point, the Sn satisfy a non-standard central limit theorem in the sense that the current scaling is n to the 3/2, and the convergent is, so the correct scaling is in the sense that is the only scaling that do not provide trivial convergence, and the limiting random variable is a real random variable which is super Gaussian, so with a density of this kind. This is the first conjecture, and I'll try to maybe say a few words. And the second conjecture is about the value of k. That we believe is this quantity, which is an explicit quantity that came up while studying the mean field model. Okay, so essentially two conjectural at criticality. This is a conjecture about the multiplicity region, and this is about the critical point. Okay, so as I said, I will say a few words. I even don't remember when I have to stop. You will tell me.
You still have 12 minutes.
Okay, so the mean field model is okay. The notation is as before. I just put a bar to distinguish the two models. Okay, so we have again a Gibbs measure on the set of configuration, and the Hamiltonian. What is the difference with the previous Hamiltonian? We have essentially replaced this term that was corresponding to the count of the triangle that create a dependence between type of edges with this mean field term. Of course, here the constant and the normalization in front are chosen suitably so that at the very end, this model displays the same free energy of the exponential random graph. In this representation, you see this sum is precisely that appear here, and here is precisely the total number of edges, and hence if we replace to this sum this u that clearly depend on x given in this way, we end up with a one-dimensional system. Okay. This one-dimensional system, and in particular the partition function that you know is related to the free energy is given in this is obtained in this can be rewritten as a sum over the parameter u, and then we have precisely this exponential, and then this is the entropic term, so the number of configuration having the number a density of edge equal to u. And now is simply by steering approximation you can rewrite this term, and you end up, you see, up to some error that at beginning is a small o and square. You have this function. This is precisely the function that we have to maximize to obtain the free energy in the exponential random graph. So the next result is not surprising, is that in fact, with obvious notation, in all the replica symmetric regime, the free energy of these two systems corresponds. For this reason, all the results that I state for the exponential, for the edge triangle model work also in this setting, okay? Because we can use precisely the same tool. We have the same tool. Free energy, Lee-Yang theorem, similar characterization of the phase diagram, at least in this replica symmetric regime, large deviation principle. Hence, we have the same results, but since it's a simple space, we can refine the results. In particular, for example, we can prove this convergence of the edge density in the multiplicity region with an explicit constant, which is the one that I gave before. These constant that depends on your actually function of u1 star and u2 star are explicit, positive. So that this case is indeed in 0, 1. and there is a meaning in the mean field setting for that, but okay. And moreover, so this is about the convergence of the edge density. The speed of convergence, we have precisely the same results, but in a strong way, because now we don't have any polynomial correction. We can say in the uniqueness region, excluding the critical point, we have a speed of convergence over the 1 over n, otherwise the critical point over the 1 over square root of n. And fluctuation of the density outside the critical point and at the critical point, maybe later. I want to maybe have been fast, but the idea that I want to convey is that we have a mean field model, which is very similar to the other one, but much simpler, and that behave very similar in all the respect that we studied. And then allows us to provide a conjecture, okay, about the edge triangle model. I want to give an idea of another way another heuristic regarding this strange behavior at criticality, non-standard behavior at criticality, and then I will conclude. So a tool that has been used along the proof that I mentioned, but that stay hidden, is large variation for the edge triangle model. So the precise statement of the large deviation, again, will require the definition of a graph limit, because it's a large deviation made state provide in this very general space. However, somehow the K tool is first a large deviation for the Erdos-Renyi graph that is given in this paper by Chatterjee and Valadan of 2011. Plus, so we have seen that exponential random graph essentially are obtained by tilting the measure of a Erdos-Renyi graph. Okay, so in fact, one can use a large deviation, so what is called the Valadan lemma, so a large deviation principle for integral of exponential functional. And from this, one can derive a large deviation for this edge triangle model. And the maximizer of the minimizer of the rate function, which is an explicit rate function in the replica symmetric region, has been studied by Chatterjee and Diaconis. In particular, they prove that in particular at criticality, the minimizer there are two minimizer. This is not true. Sorry. The two minimizer, this is not true. The two minimizer are in the multiplicity region, not at criticality. Sorry. You forget this sentence. Okay, let me go to the heuristic. The point is the following. So we want to study fluctuation. Okay. So let begin the fluctuation of our Sn with this scaling n to the 3 over 2. Now, by definition, you can rewrite this as just an event regarding the edge density, and then one can use large deviation. Since we have an explicit function for this problem, this event can be written in this way. This is explicit. If you compute it, of course, if you expand by this quantity we perform a Taylor expansion around U star, since U star is a minimizer of the rate function. Thirdly, the value of the minimizer is 0. The first derivative is 0. And in fact, it turns out that also the second derivative is 0 and the third derivative is 0. So you arrive to the fourth derivative, and this is precisely what we obtain with mean field approximation. Clearly, the problem is that we don't have any control on this quantity. While on the one-dimensional mean field model, we know perfectly what it is, and we can control it. This concludes my presentation. Thanks a lot for your attention.
Thanks, Alessandra. Any questions?
So is there a specific reason for taking your correlations like with the edge triangle function? I mean, is it because it's the smallest way of creating correlations, or could you consider taking cycles?
Okay, the edge, why do we take the edge triangle model? Okay, of course, exponential random graph can be very, very generally defined. But, you know, from the modelization point of view, you would like somehow to have minimal hypothesis, so not force too much. And the choice of triangle is quite reasonable because, okay. Yeah, I'm also looking for tracks, yeah. No, but more or less, the point is the following. In many networks, real world networks, like social network, you expect that when two individual or entities are connected to each other, so have a common friend, then they are also connected to each other. So if A is friend of C and B is friend of C, then you might expect that also A and B are connected, for example, for some certain networks. This is in a real world network, this is measured by this clustering coefficient. The point is that, for example, the Ardoshreni model, but not all, even in the homogeneous case or whatever, many classes of random graph do not satisfy this property. And so it's quite natural to try to force the system to have triangles in this sense. But I'm not, I'm not saying that is the only possible choice. And of course, the other thing is that you have two parameters. So when you start to increase the parameters meaning the edge density, the one corresponding to the edge density, the one corresponding to the number of triangles, to the triangular density. When you start to increase parameters, the problem becomes much more difficult. For example, you don't have such a characterization of the phase diagram. You know that qualitatively will be like that, but you don't know how it is done. Okay, thank you.
Any other question?
Hi, I had a question. So if you look at this as a W graphon, the limiting W graphon, then do you know what its structure is? Because there's some recent results on CLTs for W graphons, where you can see, you know, Gaussian behavior, and then you can see this chi-square behavior in the CLT. So I was wondering how this was related to
so
that.
the limiting graphon, since it's the same, so I skipped this terminology, but so the idea is very simple. Since in the limit, the measure is as in the Ardoshreni, then the graphon, the asymptotic graphon is just a constant one. Mm-hmm. So in particular, it is, indeed, it is denoted by U star, there is a theta because indeed you are in this quotient space, so that this is equal to U star, which is a solution. So it's constant. This is not the only question. This answer only one of your questions. But
yeah, because there's been some work on these W graphon models where they show that the CLT can have, depending on, actually in the homogeneous case, it's Gaussian. In certain cases and some other cases, it's going to be a chi-squared fluctuations. So I was wondering if this was resultant, but we can talk offline.
No, I completely missed this result. Thank you for pointing me.
So my question is somehow related to Sonia's question. So without increasing the number of parameters, if you just replace a triangle with a square, for example, for ages,
yeah.
Do your techniques work?
Well, not mine. So at first we have to. So for sure, the Chatterjee Diaconis techniques works well.
Oh, okay.
Okay. The mean field approximation works well. Even the theorem, so convergence and over the edge density and the fluctuation outside criticality works well. The point is that I was given this phase diagram. I don't know precisely. And since, so if I want to arrive to, so this is very general, but if I want to arrive to criticality, indeed in the paper at some point we give all kind of extension. If you want to arrive at criticality, you really need to know a specific value of your critical point. This is what gives the super Gaussian behavior, for example. So there is something that can be said in great generality, but we miss a complete picture of the phase diagram. So
okay, thanks. I think we don't have time for any further questions, so let's thank the speaker again.